Okay, today our first goal will be to find a nice relation between the left and the right higher measures on a locally compact group. But before we do it, let's discuss some basic operations on measures. Some operations on measures. Well, first of all, assume that we have a locally compact Hausdorff topological space, X. Locally compact Hausdorff topological space. And let C plus of X denote the positive code of C of X, that is the set of all non-negative continuous functions on X. So the first operation we are going to define is the multiplication by a function. So let's introduce some notation. For every linear function of I, defined as a space of continuous compactly supported functions on X. This is the space of continuous compactly supported functions. And for every continuous function f of X, we define a new functional. We define functional denoted by fi. This is also a linear functional for the same space. And we define it by the following simple formula. This functional takes every function g to I of fg. So clearly this is a linear functional. And let's observe that if I and f are positive, f is positive in the usual sense, and I is positive in the sense that it takes non-negative functions showing negative numbers, then so is fi. Fi is also positive. This is immediate from the definition. And because of this, we can transfer this operation from functionals to measures. Well, this is notation 2. So for every Radon measure, mu on X, and for every continuous non-negative function f on X, we define a new Radon measure, f mu on X as follows. The integral with respect to f mu is f multiplied by I mu. So by the representation theorem, this measure exists and is unique, because this is a positive linear functional, so it corresponds to a unique Radon measure denoted like this. In the case where X is nice, and this is emphasized for you, if
sorry, shouldn't the f be positive as well on the left one?
Here f is arbitrary because this makes sense for every function, not necessarily positive. But of course, if you want to get a positive functional, we take a positive function. And here we take a positive continuous function. So if X is sigma compact, then the measure f mu can be characterized explicitly without any reference to the representation theorem. Namely, this measure is given by the following formula: f mu of b is the integral over b f d mu for every Borel set b in X, which is quite natural. And the same is true, the same formula holds if X is arbitrary. The same is true if we don't assume the sigma compactness, but if we assume that f is integrable. But in the general case, this formula fails, and the reason is that the right-hand side of this formula is not a Radon measure. So clearly the right-hand side is a sigma additive measure on the Borel-Sigma algebra, but it is not necessarily a Radon measure. That's the problem. So if we want to define a Radon measure, we must use this formula. So we replace measures by positive functionals. Okay, one more exercise shows that the multiplication by a function, if we now consider a locally compact group, then multiplication by a function is compatible with translations. So if G is a locally compact group, f is a continuous non-negative function on G, and mu is a Radon measure on G. Then the left translate of f mu, Lx of f mu is equal to Lxf multiplied by Lx mu. And the same for the right translates. Rx of f mu is Rx of f times Rx mu for every x in G. So the multiplication of measures by a function is compatible with translations. Now, this is actually this is simple algebraic calculation, which is more or less immediate from the definition. The second operation on measures is well, let's call it reflection. Reflection. So if we have a locally compact group, so we assume that G is a locally compact group, and if I is a linear functional on the space of continuous compactly subplotted functions, then we define a linear functional S of I on the same space as follows. S of I is I composed with S. Where this here, by S I mean the usual reflection on functions, where S f of x is f evaluated at x inverse for every x in G. So clearly this is also linear functional, and clearly if I is positive, then S of I is also positive. So we can now transfer this operation to measures. So for every Radon measure mu on G, we define a new Radon measure S mu on G as follows, similarly to this case. So similarly by using the respective integration. So I S mu is S applied to I mu. Again, the right-hand side is a positive linear functional, so it corresponds to a unique Radon measure denoted by S mu. Again, it's natural to ask if there is an explicit formula for this measure. And here the situation is much easier than in the case of multiplication by a function. Namely, it's easy to show, and this is an exercise for you, that S mu of B equals mu of B inverse for every Borel subset B of G. So the situation is much easier than in this case, because in this case we have no restriction on the group. It is not necessarily sigma compact, it's an arbitrary locally compact group, and this formula holds. And finally, just like the left translation and the right translation, the reflection is compatible with multiplication by a function. S applied to f mu is equal to SF times S mu for every positive function f on G.
I'm sorry, on the right part, last exercise, do we assume G to be sigma compact or something?
No. Here G is an arbitrary locally compact group.
Yeah, but how do we define the multiplication on the measure? Yeah.
By this formula. So this definition makes sense without any restrictions on X.
Okay.
This is true for this makes sense for every locally compact space, not necessarily sigma compact.
Yeah, so
But even in sigma compact, then we have this formula. But this definition makes sense for every X. And here we mean that f mu is given by this formula.
Okay.
Okay, so now we are ready to discuss a relation between the left and right Haller measures. The relation is given by the so-called modular character. The modular character, or the modular function. The name modular function is more common, but the name modular character is more correct. First of all, because the function we are going to define is indeed a character, and second, it has nothing to do with modular forms. So that's why I prefer to use the name modular character. Okay, so suppose that G is a locally compact group, and mu is a Haller measure. Let's recall that by default, by Haller measure we mean a left Haller measure on G. And let's now observe that for every point x in G, the right translate of mu, Rx mu, is also a Haller measure. Well, indeed, why is it so? Well, this is a simple calculation. If we apply the left translate, Ly of Rx mu, then clearly left and right translates commute, so we can interchange them. But mu is left invariant, so Ly mu is mu, and we get Rx mu, which shows that Rx mu is left invariant. And clearly it is not identically zero, because mu is not identically zero. So this measure is a Haller measure, but we know that the Haller measure is unique up to a multiplicative constant. So we deduce that there exists a positive number denoted by delta of x, such that Rx mu equals delta of x multiplied by mu. And this is true for every x. This is true for every x. So as a result, you get a function which takes x to delta of x. This is a positive function, a strictly positive function of G. And this function is called the modular character. The function delta from G to the positive real numbers given by this formula. Let's denote by star. Given by star is called a modular character. The modular character, because it is uniquely determined by the formula, the modular character of G. The definition of this function can also be equivalently written in terms of integrals. proposition 1. We have the following formula. Rx I mu equals delta of x I mu for every x in G. So explicitly this means that if we apply both sides to an arbitrary continuous compactly supported function on G, then we get the following equality: f the integral of y f of yx g mu of y equals delta of x inverse to the integral of f why do I write x inverse here? Let's recall that by definition of the right translate of a linear functional, we have the following equality: R x inverse, just by definition. So if we formally apply this to function f, we must have x inverse here and x here. But I interchange x and x inverse, and I get this formula. So as a result, this formula is equivalent to this one. The proof is absolutely trivial because of our relation between operations on measures and operations on linear functionals, namely Rx of I mu is the integral with respect to Rx mu, and so this was discussed in the previous lecture, and R of x mu is just delta of x times mu. So, and the result we get the number delta of x multiplied by I mu. Okay. Let's now observe that the modular character is indeed a character. That is, it's a group homomorphism. This is proposition 2. Delta is a continuous group homomorphism from G to the group of positive real numbers, and moreover it is continuous. A continuous homomorphism. Of course, it is not unitary. It is unitary if only if it is trivial. We take G to the positive integers, but it is a continuous homomorphism. Well, the fact that it is a homomorphism is more or less immediate from the definition. Well, indeed, if we look at delta of xy and multiply it by the R measure mu, then by definition we get Rxy applied to mu. While the right translate by xy is the composition of the right translate of by x and by y. I have this formula. The Ry applied to mu is delta of y multiplied by mu. So we get this. And finally, we apply the definition of delta. Oops. Finally, we apply the definition of delta of x. And we see that this is delta of x mu. So as a result, we have delta of x, delta of y mu. So delta is a homomorphism. Well, why is it continuous? To prove the continuity, we choose a function, choose a continuous compactly supported function f on G, such that the integral of f is 1. Clearly such a function exists, because the integral is non-trivial and linear. And we simply substitute this function here in this formula. So if you apply this to f, then the right-hand side will be just delta of x. Delta of x. And the left-hand side will be Rx applied to I mu f. Rx I mu f. That is equivalently I mu applied to Rx inverse f. And at the previous lecture, we have already proved that this function is continuous. We proved this before we discussed the uniqueness of our measure. Okay, so this completes the proof. Let's now see how delta is responsible for the relation between the left and right of our measures. First of all, let's recall that if mu is a left Higher measure, then S mu is a right Higher measure. If mu is left invariant, then S mu is right invariant. And I claim that we have the following formula. This is proposition 3. S mu equals delta inverse multiplied by mu. So this is a relation between the left Higher measure and the right Higher measure. Explicitly, this can be written as follows. For every continuous compactly supported function f on G, the integral of the function f of x inverse, g mu of x, is equal to the integral over G, delta of x inverse f of x. To prove this formula, let's first of all take the right-hand side of this equality, and let's observe that this measure is right invariant. So let's note it by mu. Delta inverse mu, and I claim that mu is right invariant. To prove the right invariance, let's first of all let's make a simple little observation. The observation is that for every group homomorphism phi from G, J now show the non-zero complex numbers, we have two simple formulas. First of all, phi is an eigenvector for the right translations. We have this formula simply because phi is a homomorphism, and S of phi equals phi inverse. This is immediate from the assumption that phi is homomorphism. Okay, now let's apply this observation to showing that mu is a right invariant. Well, let's calculate Rx of mu. So this is Rx applied to delta inverse mu. We have already discussed the fact, this was a simple exercise, that right translation is compatible with the multiplication by a function. So this can be written as follows: Rx applied to delta inverse times Rx of mu. Rx of delta inverse, but delta is a homomorphism. So Rx applied to delta inverse by this formula is delta of x inverse Rx mu. Oh, sorry, delta, just delta. Yeah, we substitute delta here and delta inverse, and we get this formula. So this is the right translate of delta inverse. And Rx mu is, by definition, this is delta of x mu, by definition of delta of x. So these two guys cancel, and we get delta inverse mu, that is mu. Okay, so mu is right invariant. Mu is right invariant. Clearly this is not trivial, because mu is not trivial, and delta is strictly positive. So it is a right hard measure. And this mu is also right hard measure. So we deduce that there is a constant c, there is a positive constant little c, such that S mu equals c times delta inverse mu. And now to complete the proof, we need to show that c is equal to 1. Now we want to show that c is 1. Well, to see that c equals 1, we look at this formula and we apply, first we multiply both sides by delta. Multiplied by delta, and we, let's note it by formula 1. So first of all, formula 1 implies that c mu equals delta multiplied by S mu. So we simply multiply this by delta. On the other hand, the same formula implies the following. So let's now do another trick. We apply S to both sides of this formula. So if we apply S here, we get just mu. And if we apply S here, we get C times S applied to delta inverse mu. Now again, let's recall that S is compatible with multiplication. So we can write this as follows. What is S of delta inverse? We'll look here. We'll substitute delta inverse here, and we see that S of delta inverse is just delta. C delta S mu. But we now look here. Delta S mu is C mu. We substitute this here, and we get C squared mu. So mu equals C squared mu, and C is positive. So C is 1. And this completes the proof. So now we come to the following definition. We say that G is unimodular if delta is identically 1. So equivalently, this means that a left-hand measure is right invariant. Or the other way around. Equivalently, we can say that the right-hand measure is left invariant. This is the right-hand measure is left invariant. This is a rather big class of groups. First of all, it's clear from the definition that an abelian locally compact group is unimodular. Well, it's clear from the definition. If it is abelian, then of course the left and right invariance properties are equivalent. A bit more interesting is the following example. Let's observe that every compact group is unimodular. Well, indeed, why is it so? Well, we know that delta is a continuous group homomorphism from G to the positive real numbers. So the image of a group homomorphism is a subgroup. And since G is compact, delta of G is also compact. So as a result, we see that delta of G is a compact subgroup. A compact subgroup of the group of positive real numbers. And it's immediate to show that this is the only compact subgroup of this group is identically 1. So delta is identically 1 and the G is unimodular. It turns out that all semi-simple new groups are unimodular. This can be shown by reducing to compact groups. More generally, all reductive Lie groups are unimodular. On the other hand, all nilpotent Lie groups are unimodular. But at the same time, not all solvable Lie groups are unimodular. And actually, we already have an example of the situation. This example, at the same time, exercise 3. Let's look at the group of affine transformations of the real line, which was discussed at the previous lecture. So it can be interpreted as the group of 2 by 2 square matrices of the following form, where A is an non-zero real number, and B is also an arbitrary real number. So this group is not unimodular. In fact, we can explicitly calculate the left and right parameters and to see that they are different. So it is not unimodular. Well, in the case where G is a Lie group, there is an explicit formula for the modular character, which looks as follows. This is also an exercise for you. Suppose that G is a Lie group. And let G Gothic denote the tangent space at the identity. So you probably know that this space has the natural structure of Lie algebra, but at this point this is not essential. We look at this object just like as a vector space. So for every point x in G, let's look at the corresponding inner automorphism of G, the inner automorphism Rx. It's from G to itself by the following formula. It is smooth, so we can take the differential of this map. Let's take the differential at the identity and let's note it by AD of x. So this is the differential of Rx at the identity. And this is a linear map from G Gothic to itself. This makes sense for every x, so we get a map AD from G to the general linear group of G Gothic, the group of invertible operators on the space. And this map is easily seen to be group homomorphism, which has a special name. It is called the joint representation of G. The joint representation of G. So the exercise is to prove the following formula. The modular character, delta of x, is the absolute value of the determinant of ADX inverse. So this is an explicit formula for the modular character of an arbitrary Lie group. To complete our discussion of the modular character, I'd like to warn you that there is a different definition in the literature. So some people introduce the modular character as follows. Was denoted by delta tilde. So in some books and papers, you'll find the following definition of a modular character, delta tilde. Of course, it is related to our delta in the following obvious way. But be careful. If you meet somewhere this object, be sure that just check what the author actually means. Which of the two definitions is adopted by the author. Okay. Some time ago, I already told you that a very important tool in harmonic analysis is the theory of Banach algebras. So let's now forget about locally compact groups for a while, just for a while, and let's discuss the basics of Banach algebras. The basics of Banach algebras. So let's recall that by default, all our vector spaces and algebras are overly complex numbers, and by an algebra, we mean an associative algebra, but not necessarily unital. So we don't assume the existence of the identity element.
Вы сказали, что каждая группа Ля не модулирует.
Не, я такого не говорю.
Вот как раз
Не.
третий пример как раз говорит.
Нет, конечно.
А вот, сейчас вот последнее упражнение выяснится, что вот здесь вот константа. Все, я понял.
Okay, so let's define normed algebras. By definition, a normed algebra is an algebra A. Algebra A equipped with a norm so it is an algebra and a normed space at the same time, such that the norm is compatible with the multiplication in the following way. The norm of AB is less than or equal to the norm of A times the norm of B for every A and B. So in this case, we say that the norm is submultiplicative. The norm is submultiplicative. If our A is unital, then we also require that the norm of the identity element is equal to 1. If A is unital, then we require that the following formula holds, which is also quite natural. To understand where the submultiplicativity condition comes from, I suggested the following exercise. The multiplication of a normed algebra is continuous. This readily follows from the submultiplicativity property. And in fact, a kind of converse is also true. I won't write this down explicitly, but the point is that if we have an algebra with a norm, and such that the multiplication is continuous, the norm is not necessarily submultiplicative, but we can always replace it by an equivalent norm, by a norm which gives the same topology, and which is submultiplicative. So this submultiplicativity condition is essentially equivalent to the continuity of the multiplication if we just consider norms up to the obvious equivalence relation. So if the multiplication is continuous and if we replace a norm by an equivalent one, then we get a submultiplicative norm. Okay, let's now look at some examples of Banach. I forgot to explain to say what a Banach algebra is. So of course, a Banach algebra is a complete normed algebra. Banach algebra is a complete normed algebra. So let's look at some examples of Banach algebras. Well, first of all, we'll have a stupid example. Example 0. The zero algebra and the complex numbers are clearly Banach algebras. By the way, both of them are unitary. The zero algebra is also unitary for trivial reasons. In this case, the identity is equal to 1. The identity is equal to 0. So this is algebra unitary. Most concrete interesting examples of Banach algebras can roughly be divided into 3 classes, namely function algebras, operator algebras, and group algebras. Of course, these classes are not disjoint, so sometimes function algebra can be represented as an operator algebra, and in other cases, a group algebra can be represented as a function algebra, and we will meet such situations fairly soon. In this course, we are mostly interested in group Banach algebras, that is, in Banach algebras associated to locally compact groups. But function algebras and operator algebras will also be important for us. So before we construct group Banach algebras, let's look at some concrete examples of function algebras. Example 1. If x is any set, then L infinity of x, the space of all bounded functions on x, is a Banach algebra. Under the pointwise multiplication. Well, clearly this is a Banach space for the supremum norm, and it's an algebra under the pointwise multiplication. And the submultiplicativity is immediate. If moreover x is a topological space, this is example 2, then we can consider the subalgebra in L infinity of x consisting of continuous bounded functions. If x is a topological space, then we denote by CB of x the algebra for continuous bounded functions on x. It's a standard fact that this is a closed subalgebra in L infinity of x. Closed subalgebra in L infinity of x. So it is a Banach algebra. This algebra has a useful ideal consisting of functions vanishing at infinity. So let's give the following definition. You have a continuous function, f on x, where x is a topological space. We say that f vanishes at infinity. Vanishes at infinity. If for every positive epsilon, there is a compact set K in X, such that F is less than epsilon outside K. Well, clearly, if X is the real line, then this means precisely that f vanishes at infinity in the usual sense, that is, the limit of f at infinity is 0. And we denote by C0 of x, and this is our example 3. Example 3, C0 of x is the space of all continuous and vanishing at infinity functions on x. It's easily seen that this is closed ideal in CB of x. Closed ideal in CB of x. So in particular, this is a Banach algebra. Of course, this algebra is not necessarily unital. If x is not compact, then the function which is identically 1 doesn't vanish at infinity, and this implies that this algebra is not unital. Of course, if x is compact, then C0 of x equals CB of x. Because there is no infinity in the compact space. And this is just this algebra of all continuous functions on x, because every continuous function is bounded. But if x is not compact, I'd like to stress that if x is not compact, then C of x doesn't have a natural structure of a Banach algebra. It has a natural topology, but it doesn't have a natural norm. So C of x, in general, C of x is not a normed algebra. Example 4. If we have a measure space, x mu, measure space, then we can look at the space L infinity of x mu, of equivalence classes of essentially bounded measurable functions. And this is also an algebra under pointwise multiplication. And it's a simple exercise to show that the natural norm, that is the essential supremum norm on this space, is submultiplicative. So this is a Banach algebra under pointwise multiplication. This is a simple exercise for you to show that the norm is submultiplicative. Example 5. Let's now look at the space of n times continuously differentiable functions on the interval AB. By the way, this is also a little exercise. So I claim that this space, this algebra is a Banach algebra with respect to the following norm. The norm of f in this algebra is the following sum from 0 to n. We'll take the kth derivative of f, calculate the supremum norm of the derivative, and divide it by k factorial. This norm is equivalent to the most standard norm on this algebra, defined to be the maximum of the supremum norms of the derivatives fk, where k runs from 0 to n. So this norm looks more natural, but this one has the advantage of being submultiplicative. This is a simple exercise. This one is not submultiplicative. Example 8. Oh, example 6. Yeah. Example 6. Suppose we have a compact subset of the complex plane, K. Compact set. And let the node by A of K. The algebra consisting of various continuous functions on K, which are homomorphic on the interior of K. Homomorphic of the interior of K. It's easily seen that this is a closed subalgebra in C of K. Closed subalgebra. This really follows from some elementary properties of homomorphic functions. So it is a Banach algebra. And an important special case is the case where K is the closed unit disk on the complex plane, was denoted by D. D bar is the closed unit disk the complex plane. And the algebra A of d bar is called the disk algebra. This is one of the standard examples of Banach algebras consisting of holomorphic functions. Let's now look at two standard examples of operator algebras. Example 7. If E is a Banach space, then we can take the algebra of all bound linear operators on E, we denote it by script B of E, the algebra of bounded linear operators on E. And the standard fact that this is a Banach algebra under the usual operator norm. The operator norm is known to be submultiplicative, so it is a Banach algebra. Now this algebra contains a classical closed ideal consisting of compact operators. This is example 8. Example 8. Let K of E denote the set of compact linear operators on E. It is well known that this is a closed two-sided ideal in B of E. So in particular, this is a Banach algebra. Again, if E is infinite dimensional, then this algebra is not unital. The identity operator is not compact. But this is a very useful Banach algebra. Some algebras that we've just considered, some of them have a useful extra structure, namely an involution. Let's give the respective definition. If A is an algebra, not necessarily a Banach algebra, just an associative algebra over the complex numbers, then by definition an involution on A is a map from A to itself, which takes every element in A to another element denoted by A star, such that the following axioms are satisfied. First of all, this operation is an involution in the usual set theoretic sense. That is, if we apply it twice, then we get the identity map A double star equals A. Second, it is antilinear over the complex numbers in the sense that we have the following identity: lambda bar A star plus mu bar B star, where lambda and mu are complex numbers. So it is antilinear. And finally, it is a ring anti-homomorphism. That is, A B star equals B star A star. An algebra equipped with an involution is called a star algebra. Now, algebra A equipped with an involution is a star algebra. Well, so far this is a pure algebraic notion. If A is equipped with a norm, so it is moreover a Banach algebra, then again it is natural to require that the involution be compatible with the norm. And we come to the following definition. By definition, a Banach star algebra. A Banach star algebra is Banach algebra A equipped with an involution a Banach algebra equipped with an involution such that the involution is isometric. The norm of A star equals the norm of A. And finally, we say that Banach star algebra A is a C-star algebra you will have the following relation. The norm of A star A is equal to the norm of A squared for every A in A. And this identity is sometimes called the C-star axiom. The C-star axiom for A. This property is very important. In fact, the theory of C-star algebras is very deep and rich, and in fact is much more interesting and much richer than, for example, the theory of Banach star algebras. So we add a little axiom and we get something much more interesting. In fact, the theory of C-star algebras is one of the most interesting and rapidly developing fields of modern functional analysis. If you look at archive.org, the well-known preprint site, there is a special subject classification for operator algebras, and it is even more active than the subject classification of functional analysis. So the number of papers or preprints published in the section of operator algebras is essentially bigger than the number of papers published in the rest of functional analysis. C-star algebras are not the main heroes of our course. We will be mostly interested in group Banach algebras, but nevertheless they will play an essential role, in particular when we discuss some properties of the Fourier transform. Well, some more definitions. If we have a homomorphism between star algebras, it's essential to consider those homomorphisms which preserve the involution. So you have two star algebras A and B, star algebras, then an algebra homomorphism phi from A to B is called a star homomorphism. A star homomorphism. Even is compatible with the involution in the following sense: phi of A star equals phi of A star. And one more notion: if A is a star algebra, then we say that a subset S of A is a star subset if it is stable under the involution. If for every A in S we have A star belongs to S. So briefly, this means that S star equals S. In the same way, we define star subalgebras. A star subalgebra is a subalgebra which is a star subset. And it's clear that a closed star subalgebra of a Banach star algebra is also a Banach star algebra. And that a closed star subalgebra of a C star algebra is a C star algebra itself. Okay, let's now look at some examples of Banach star algebras and of C star algebras. Again, it's clear that the zero algebra and the complex numbers are C star algebras. The involution on the complex numbers is just the complex conjugation. If we look at the Banach function algebras that we've just discussed, then most of them are Banach star algebras. L infinity of x, the algebra of bounded functions on a set, the algebra of continuous bounded functions on a topological space, C0 of x, the algebra of continuous functions vanishing at infinity, L infinity, the big L infinity space over measure space x mu, Cn of AB, the algebra of n times continuously differentiable functions on AB. All of them are Banach star algebras with respect to the involution, which is just the pointwise complex conjugation. The pointwise complex conjugation. Moreover, all of them except Cn of AB are actually C-star algebras. This is a simple exercise for you. As for Cn of AB, it is a Banach star algebra, but it is not a C-star algebra if n is positive. This is also an exercise. Cn of AB is not a C-star algebra. If we now look at the disk algebra, the algebra of continuous functions on the closed disk, which are holomorphic on the open disk, this algebra also has the structure of a Banach star algebra. Example exercise number. We don't have numbers here, just example and exercise. The disk algebra A of D bar, is a Banach star algebra with respect to the following involution f star of z. Well, of course, we can try to define the involution in exactly the same way as here, but this is not defined because f of z bar is not holomorphic. It is any holomorphic. So to get something holomorphic, we put one more bar here. We take the complex conjugate of this function, and this is holomorphic on the interior. And it's a simple exercise to show that all axioms of a Banach star algebra are satisfied. So this is a Banach star algebra. But it is not a C-star algebra. But it is not a C-star algebra. Also, there are important examples of operator C-star algebras. Namely, if H is a closed space, then VOH, the algebra of bounded linear operators on H, is a C-star algebra. Here, the involution is just the usual operation of taking the adjoint operator. Let's recall that the adjoint operator of a Hilbert space of a bounded operator T on a Hilbert space is uniquely determined by the following formula. And the standard fact of functional analysis is that the C-star axiom is satisfied. So this is the C-star algebra. And the compact operators, the set of compact operators is a closed two-sided star ideal. A closed star ideal. So it is stable under the involution. So it is also a C-star algebra. VOH is a C-star algebra. Okay, let's now turn to group Banach algebras. In functional analysis, in contrast to pure algebra, there are many ways of associate an algebra to a locally compact group. So we'll discuss only two of them: the algebra L1 of G and the measure algebra, which consists of complex Raban measures. But also there are other choices depending on the group. In fact, the general ideology here is that different types of group algebras are responsible for different types of representations of our group. Okay, so let's start with the Banach algebra L1 of G. Before we define this algebra, let's discuss some properties of Rodin measures on locally compact spaces. The following proposition 1. Suppose that we have two locally compact spaces x and y, and we assume that they are second countable. Second countable locally compact topological spaces. Hausdorff locally compact topological spaces. I claim that the Borel sigma algebra on their product is generated by the set of all rectangles of the following form, B1 cross B2, where B1 and B2 are Borel subsets of x and y respectively. And second, if we have two Rodin measures, mu is a Rodin measure on x, and u is a Rodin measure on y, then the product measure, m tensor u, is also a Rodin measure. Rodin measure on x cross y. Well, probably it would be better if I move 1 from here to here. So in both cases, we assume that x and y are second countable. The proof is a rather straightforward exercise in measure theory. Nevertheless, I'd like to point out that if x and y are not second countable, then property 1 fails. So in general, the set of all Borel rectangles generates a smaller sigma algebra than the algebra of all Borel sets. And as a result, if x and y are not second countable, then statement 2 makes no sense. Because, in all standard courses of measure theory, the product measure is defined on the sigma algebra generated by such rectangles. So this measure is simply defined on a smaller sigma algebra. So we cannot look at this measure as a Borel measure. In fact, there is a way out of the situation, which enables us to speak of product measures on arbitrary locally compact spaces, not necessarily second countable. But I wouldn't like to spend too much time on measure theoretic technicalities here. So when it's convenient, we'll always assume that our spaces and groups are second countable. This is quite a natural assumption, which is satisfied in many concrete examples. Proposition 2 deals with hard measures. Proposition 2. You will have two locally compact groups, G1 and G2. Locally compact groups. And mu1 and mu2 are measures, G1 and G2 respectively. We also assume that they are second countable. So we may consider the product measure, which is also a Rodin measure on the product. And I claim that this is the hard measure on the product. mu1 tensor mu2 is a higher measure of the product. This is a very easy exercise for you. So proposition 1 implies that this is a random measure, and the left invariance is quite immediate. The left invariance of the product measure follows from the left invariance of mu1 and mu2. Okay, so our next goal will be to define the Banach algebra L1 of G. There is a little technical point here, because we want to define the convolution on the space of integrable functions on G, and to define the convolution, we must be sure that some function which appears in the definition of the convolution is measurable. This is not entirely obvious, so let me write this down explicitly. At least I'll give you an unexpected statement, and the proof will be given at the next lecture. So suppose that G is a locally compact group, and mu is a hard measure on G. Let's denote by mu the set of all mu measurable subsets of G. By H. The collection of all mu measurable subsets. Let's recall standard factor measure theory that this set is a sigma algebra, and it can be interpreted as the completion of the Borel sigma algebra. Explicitly, it consists of all sets of the following form, which is the union of a Borel set B and a mu null set N. A mu null set. So this is the completion of the Borel sigma algebra. So when we work with integration, it's always convenient to work with the completed sigma algebra because it has the advantage of being complete. That is, a subset of a null set is measurable and is also a null set. This is a convenient property when we work with integration. So we have the following lemma. Suppose we have two measurable functions, f and g, on our group. I mean, they are measurable with respect to this completed sigma algebra. I claim that the following function, let's denote it by big F, it is a function of the product of G by itself, and it is given by the following formula: F of y, G of y inverse x. You probably remember that when we discussed convolution on the circle and on the real line, this function appeared in the definition of the convolution. So for technical reasons, it is convenient to prove that this function is measurable. And I claim that it is measurable. F is measurable with respect to the product measure mu tensor mu, which is the hard measure on G cross G. Let me stop here. So the proof will begin at the next lecture. but just a short announcement after we prove this result. We'll be able to define a convolution of two measurable functions on our group by the following formula. dv of y. And we will see that if f and g are, if both functions f and g are integrable, then their convolution is defined almost everywhere. It is also integrable, and it makes L1 of g, the space of integrable functions on g, into a Banach algebra, into a Banach star algebra. So this will be our first goal for the next lecture.